Hello everyone, welcome to our session. In this session, I will talk about virtual machines live migration on Arm cloud infrastructures. This session will be divided into two parts. In the first part, I will talk about some background information and the main gap between migration on Arm and x86 platform, and what kind of improvements did we done in the past few months to close the gaps. And in the second part, Kevin from Linaro will go to details about live migration process. Before we go to the content, please let me introduce myself. My name is Zhenyu Zhang. I'm from Huawei. I'm the contact person of ARM open source ecosystem of our department. I've been working on open source for about 6 years, and here is a QR code for our Slack channel we created for discussion about ARM server ecosystem. Please join if you are interested. Okay, so let's start. The first thing first, what is live migration? In the cloud world, migration normally means process of moving virtual machines of or application between different physical hosts. Like shown in the graph on the right, yellow VM will be migrated from host A to host B. And live migration is one of the forms of migrations. When migration process is performed on running virtual machines and applications, and the process can be done without disturbing the workloads, it can be called live migration. Migration and live migrations are very important for cloud users. So what are the typical use cases for live migrations? Here we have two examples. The first example case is for hardware maintenance. In the production deployments, the cloud provider will always have to perform hardware maintenance sometimes. For example, hardware and software upgrades or the replacement of broken hardware. When performing the maintenance, we do not want to disturb our cloud users because one of the reasons people use cloud is to avoid hardware failures. So the cloud provider will have to live migrate all the VMs on host A to host B before hardware maintenance without disturbing the running VMs and the applications inside them. The second use case is also very common. A live migration can be used to perform load balance on cloud infrastructures. In the production deployments, sometimes due to some reasons, for example, some VMs on host B got deleted or migrated to other hosts, causing the workloads on different hosts unbalanced. So the load on host A is much higher than host B. So as the cloud provider, I may want to balance the load to give each VM better performance. This will be also need the help of live migration. Also, sometimes the cloud provider will want to do the offset to save power. They will want to live migrate the last VM on host B to host A and then turn host B into sleep mode to save power. All this is due to cloud providers' dynamic resource allocation policy, but it will need live migration as the underneath technology. And there are also many other cases for live migrations. We will not cover them here. So before we go to the comparison between ARM and the x86 platform, I would like to go through a little bit about the main process of typical migration process. We will only look at some basic ideas here. The implementation details will be discussed by Kevin later. So we take OpenStack as an example. We will have a controller accepting users' API calls and manage the cloud. And the VMs are running on compute host. When user call for live migration, the controller will receive the call and perform pre-migration actions. This will normally include finding the suitable destination. If the user did not provide a target destination, the controller will calculate a suitable one. If the user provides the destination host, the controller will check if it is suitable. After this check, the controller will ask the source and the host destination to start the migration process. In this part, we will mainly focus on the check actions. We will compare the Libvirt codes on this. Libvirt is one of the most widely used open source management toolsets for management platform virtualizations. It is used in OpenStack, Ouvert, and many other cloud platforms. By comparing the Libvirt code for Arm and X86 driver, since we have done some improvements in 6.4.0, so first look at the code prior to 6.4 here to see the gaps. We can easily see 3 gaps here. The first one is general. We can see that x86 driver has over 3,500 lines of codes, and the ARM driver only have 265 lines of code. And that's very huge difference. We can easily see how big the gap is just by thinking about the code line difference. The rest two are related to migration directly. The second one is the missing of getHost function. This function will be used to provide host CPU details, and this information will be used to track whether the host is suitable for VM migrations. If this is missing, then we cannot perform the check. The third one is the CPU compare function. We can see that ARM driver have a CPU compare function, and it seems okay. But when we check the details for this function, we can see that in ARM driver, there are no actual checks. Identical was returned directly. And this also proves that if there are no host information gathered, the check cannot be performed. On the contrary, in the x86 driver, there are much more related lines of code and performed much more complicated checks. If we cannot provide the checks in the code and return directly as the code does it now, the upper layer cloud platforms, in the upper layer cloud platforms, the cloud provider will have to manually set rules for all compute hosts. This will be a disaster for the large deployments. So we want to change the situation. So we did some improvements. The first one has already been merged and released in Libvirt 6.4.0. We can now gather and report CPU information on ARM platforms. The information includes CPU architecture, model, vendor, CPU flags, and others. And this will provide enough information for CPU checks in migrations. The other one we are currently working on is to provide the CPU compare support in ARM. In the first step, we will compare the source host CPU info with the destination CPU info. As in most real-world deployments, people use host pass-through mode for ARM VMs. After this is done, the life of cloud provider will be much easier. Okay, so this is for our first part of the session. Kevin will give you more details about live migration and how it is performed in the second part. Thank you.
Okay. Thanks for everyone for continue listening our session. And thanks Zhengyu for talking about the live migration in the Libvirt side. So next, we will talk about the live migration on the infrastructure as a service side. So first, to generally introduce myself, my name is Kevin Zhao, and I'm now focusing on the OpenStack and the Kubernetes development. And now I'm working at Linaro LDCG. Okay, so as we see in this picture, so the live migration functions are generally need to support both on the Libvirt and also need to on the hypervisor side, and also in the high level infrastructure as a service side, for example, the OpenStack or the Vault Manager, they also need to support the live migration feature. So here, we will take the OpenStack as an example to elaborate the details. Because the OpenStack is generally the open source infrastructure as a service framework now, and it has achieved a lot of success in the private cloud area. Also, in the Arm64, we only support the Libvirt plus QEMU KVM instance. So we will talk. Our talk will be limited to this area. So we can see the OpenStack has a compute project called NOVA. It is served as a Libvirt client, and when migration, it need to control and monitor the whole migration process, and also deal with the CPU features or deal with the network problem or the storage problems, and to control the whole process. So now we will dig into this process to see the mechanism of LAN migration. For NOVA, it has support three methods of migrate. The first is, we know it is a non-LAN migration. It is a code migration, so when migrate, the instance will be suspended for a while. So, and there are two methods of LAN migration. The first is a block LAN migration, and the second one is a true LAN migration. The difference from them are the whether we have a shared backend storage for the instance. So for example, so in the block LAN migration, the instance storage are not have a shared volume. So we need to copy the whole instance disk from the source node to the destination node. So it will take a bit long time and return. So on the real LAN migration, based on the shared volume or shared backend storage, it requires both the dist and the source node can access the instance disks. For example, we can use the NFS, or such as the external distribute system, such as the Ceph. So for example, in our Linaro developed cloud, we are using the Ceph as the backend storage for the instance. So the migration time will be reduced, since the migration process only need to deal with the dirty memories and no need to change the instance disk. Okay. Here we can see there are two paths we need to consider. First is the control path, and the other is the data path. We can see in this picture, the control path and data path, the source node here, we can see the picture here. So the source node hosts are running Libvirt, and the dist node are also running Libvirt. So both of them are controlled by OpenStack, and both of them are served as a compute node. So now the NOVA as a client to talk with Libvirt to control the migration flow, and we want to migrate the VM3 from source node to dist node. In the control path, NOVA will serve as a client and to control the migration process. So in the control path, NOVA will monitor and trigger all the migration process. And in the data path, it has been separated to two methods. So one is a hypervisor native direct data transport. So if we want to enable this, we need to set the migrate flag to peer-to-peer. So if we want encryption, it all depends on the hypervisor, whether hypervisor supports the encryption. And the other is the Libvirt kernel. So Libvirt will establish a RPC between the source and host, and it can support encryption due to Libvirt features. So if we want to enable this, we need to set the live migration kernel D to true in the NOVA. Okay, next. We can see it is a generally 5 phrase for the live migration. So in the pre-level, we can see there is a active virtual machine A on the physical node A. So, and we want to migrate the virtual machine A to another node, and the scheduler has selected the node B as the live migration destination. So in the reserve side, it will call the method as a host B to confirm the B has the available resources and then trigger the migration process. So there is one thing we need to consider is keep the network info, because we want to the VMA hosting at node A and then migrate to the VMA hosting at node B. So the network info are the same. It needs to keep the same network NIC, MAC address, and the IP. So from the source host, we need to get the metadata, and then on the dash node, it will set up a virtual machine NIC on the node B and plug it into the BRINT bridge. We know that the BRINT bridge is an eternal OVS bridge, and after reserve, we will have a new VM post on the node B. Next, we will enter into the more complicated area we call the iterative pre-copy method. So in this phrase, we know first, the hypervisor will mark all the memories on the VMA as dirty memories, and then it will iterative copy its memory from the source node to the destination node. And the Libvirt will and NUMA will monitor the RAM during the copy process and then copy the data pages to the destination. It will be an iterative method and doing the things iteratively. So as we see and as we expect, the data pages will be reduced during the copying. And we know that the RAM is changing every time. So during the copying process, the original virtual machine also will be, the memories in the original VM also will be changed, and it will be marked as data pages. So we cannot guarantee that we can enter into a phrase that all memories are synced with the destination virtual machine. So we should set the downtime threshold. So this threshold is the time period we will meet when suspend the VM and copy the last memories. So when migration, it's easy to calculate the time according to the remaining dirty pages and bandwidth. So which is very significant signals for stopping the iterative process, because when the calculating time is less than the threshold, Libvirt will trigger the next phrase we call stop and copy phrase. So NUMA has set up the downtime threshold. So and when the downtime threshold meet our needs, the Libvirt will stop the VM and copy the remaining dirty pages to node B. So next, we will come to the last two phrases. We can see the max downtime that calculated is less than the long migrate downtime flag. Libvirt will suspend the VM and then copy the remaining dirty pages one time directly to the node B. And then Neutron will unplug the virtual machine interface from the VMA and node A. And also in the host B, because that the primary host for VM in host B, it has become the primary host for the VMA, and the Neutron will plug into the virtual machine interface. Plug into the virtual interface to the virtual machine, newly virtual machine, and then triggering the booting process. Also, there is a flag we can see, it is called auto converge. Let's assume a high overload virtual machine whose memory is changing rapidly and take a pressure loading. So when migration, the dirty pages are hard to reduce. So and induced our migration process lasting for a very long time, or maybe induce a long migration field. So we can choose this flag, and it will change the virtual CPU to reduce the load pressure in order to reduce the newly generated dirty pages. Okay, we can see the long migration things we need to consider is a CPU, different CPU. As Zhengyu said before, the migration from A to B is fine due to that the CPU instructions are the subset of the node B, but in the comparison from B to A, it's failed. So this is a very important things we need to enhance in the Libvirt level. And now in OpenStack side, we just skip this check to make the lab migration happen. The last things we need to consider is the NUMA. As we know, NUMA topology is so the NUMA topology is another things. Here, we need to triggering the lab migration. We need to consider in triggering the lab migration. The Libvirt and Kubevirt are generally doing what NOVA tells them to do. So actually in the old version of NOVA, when they migrating, the CPU pinning information and the NUMA top will be kept from the source to destination after lab migration. So NOVA is generally the NUMA non-vir to some extent. So as we see, this is a NUMA XML and it will be naively copied to the destination. So that will induce a problem because we have set the CPU pinning in the node A, and the pinning map will be naively copied to the destination node, and any existing pinning mappings on the destination node will be ignored. So that will induce a problem because if there is another instance already existing on the destination, so both instance vCPU has been pinged to the same vCPU, same physics CPUs. So that will make the performance issues. So in order to solve this problem, NOVA has introduced a new NUMA aware lab migration. We can see a totally workflow. So after the scheduler choose the destination, it is before the pre-migration. The NOVA conductor will check the lab migration in destination node, and the source node will send the migration data plus the instance NUMA topology. So this here, the instance NUMA topology is information from the source and to the destination node. And in the destination node, it has maintained a NUMA topology itself. So after that, NOVA will do the logical to feed the instance NUMA topology according to the NUMA topology in the destination node. And after that, it will check if the destination will meet the request. So if fail, our lab migration will fail. And if succeed, it will return the new instance NUMA topology to the NOVA conductor. So, and after that, the conductor will trigger the pre-lab migrations with the newly fitted instance NUMA topology to the source node. And then the source node will use the newly instanced NUMA topology to call the Libvirt driver to generate the new NUMA the NUMA XML for the destination. So the NUMA topology will be changed according to the newly destination node, and it will make sure that it suits our need and didn't trigger the problem as we referred before. Okay, thank you for listening to our session.